All right, let's get going. Well, welcome everybody, and thank you for attending our CUIIC Academy Underground webinar today. Today is World Trenchless Day, so we thought we would do a topic on trenchless, and we are going to focus on pipe bursting overview and a case history presented by David O'Sullivan. Next slide. As I said, this is organized by the Canadian Underground Infrastructure Innovation Centre. I think I already said this, for short, CUIIC, based out of the University of Alberta, combined with Benjamin Media. CUIIC Academy also offers classes, courses, webinars, and other events to further underground infrastructure educational opportunities. And the goal is really to reach across all of Canada. And as part of that, you're here because this is one of our many presentations in a broader webinar series. The webinars happen every third Thursday of the month, and our installment today, as I said, it's World Trenchless Day, so pipe bursting. We try to do a range of topics, and if for full information, you can visit, for upcoming and past webinars, you can visit the CUIIC Academy website for more information. Lots of good stuff there. Some other CUIIC Academy events, just to reach out there, because I think we have an audience that would be interested today. Save the date for the 2025 Pipeline Rehabilitation Academy. This is an in-person event, and it's on scheduled for March 5th and 6th, 2025 in Mississauga, Ontario. This was held 2 years ago, and it was a really great turnout. So we're updating the outline and the course material. So again, look forward to that. I think it's going to be a great event, and put that in your calendar. We'd like to give a big thank you to our 2024 webinar series sponsor, Westlake Pipe and Fittings. Okay, and with that, I'm going to get ready to hand it over to David O'Sullivan, who is our presenter today. David completed his engineering from 1974 to 78 in Ireland before coming straight to Canada. He worked in the consulting industry business for 7 years before switching to the contracting industry in 1986. He has worked in the utility industry since 1986 and was instrumental in introducing microtunneling, large diameter HDD, slip lining, and pipe bursting into British Columbia marketplace in the last 20 years. He now is president of a leading trenchless company in Western Canada, completing numerous pipe rehabilitation programs for various government bodies. So we have a very knowledgeable and experienced speaker today, and on that, I'm going to hand it over to David to tell us, give us an overview on pipe bursting. So take it away, Dave.
So I am on now. Yeah, okay.
Yes.
I'm David O'Sullivan. I'm going to talk today about pipe bursting. Given the age that I'm at, I remember back in the days when slide rules were existing. So I'm a bit of a Luddite in computers, but I should be fine. Okay. Pipe bursting, just the basics. We're just going to talk about the basics in pipe bursting. I would strongly recommend, if you're a consulting engineer or you're a city engineer, that you continue on and do courses either with NESTT or other entities. They're, more in-depth courses. This is just a flavor of what pipe bursting is. Okay, pipe bursting came out of a requirement in Britain in the early 70s, when Britain discovered natural gas in the North Sea, and they started transferring their gas system. They used to have a coal gas system. They started transferring their coal gas system to natural gas, and discovered that the cast iron gas mains all over Britain had this beautiful tar coating on the inside of the gas pipelines, of the cast iron pipelines from the coal gas. But when they put natural gas in there, the natural gas dissolved the tar, And you had gas coming out of the pipelines everywhere, so they had to come up with a quick way of replacing those pipes as fast as possible. And they worked with a company called D.G. Ryan and developed pipe bursting. At that point, it was pneumatic pipe bursting that they worked with. Next slide. Caroline, I'm not seeing the slides.
I can see them.
Yeah, I can't. Okay, anyway, I've got them here. This is the second slide. Bursting types.
Bursting types and materials that can be burst.
Yeah. Okay, bursting type. So there's two basic types of pipe bursting that now exist. Pneumatic and static. There used to be other methodologies called hydraulic, and there were chain systems. There was lots of different types of bursting, but they've tended to fall by the wayside. As I said, British Gas was the instigator of pipe bursting way back. And when I started in pipe bursting, we actually had to pay a patent fee to British Gas. You can see on the right-hand side of that slide, there is a picture from TT Technologies, and it shows the various materials that can be pipe burst. Now, that statement is not quite true, because that list of materials there, if I'm looking at it, the top one is cast iron, concrete, clay, reinforced concrete, and asbestos cement. Those can be pipe burst. Steel, truss, corrugated steel, ductile iron, and plastic really can be pipe split. And there is a difference between the two, and we'll talk about that in a few minutes. Next slide. Alison, I do not see any slides here. I'm sorry.
Sorry, David. Did you try to press the slides button at the top? We're on slide 10. Why do we rehabilitate?
Yeah, I am looking at the... Sorry, Alison.
That's okay.
Ah, that's what I'm looking for. Thank you. Why do we rehabilitate? Well, Alice and I were having a conversation about this a few minutes ago. First of all, let's go back and discuss what is a pipe. There are three conditions that I would consider paramount to looking at a pipe. First of all, it's a vessel that contains a liquid. That's the problem that British Gas had. The pipes were of sufficient capacity, but they no longer contained the liquid or the gas in that case. So therefore, they failed in that point, from that point of view. But the hole was still in the ground. There was still cast iron there. So it succeeded in conditions 2 and 3, but it failed in condition 1. Condition 2 I'm talking about is its ability to transport a liquid. In other words, is it big enough? And then the third one is a structure. It's a structure to maintain a tunnel. Does it have the ability to maintain the tunnel? That's more evident on corrugated steel pipes and large culverts, and also in clay pipes. Clay pipes tend to fail longitudinally. We'll talk about that in a few minutes. So pipe bursting mainly deals with that second condition, which is the condition that the pipe is undersized. It solves that problem. If you want to go back to condition 1, which is the leaking, you can line the pipe with CIPP liners, or you can do sprayed and place liners, or you can slip line. There's lots of solutions for that. But mainly the only solution we really have for a pipe that's undersized is to pipe burst it. So essentially what we're doing is we're using the hole that exists in the ground and upsizing that hole. Now the hole that we're generally, when we talk about upsizing the hole, to go, the 25% is common, but the problem is 25% is a very small upsizing in hole. If you look at a standard upsizing, which say 200 to 250 or an 8-inch to 10-inch upsize, that's a 50% increase in size. And if you're going 150 millimeters to 300 millimeters, that's a 400%. That's a very large upsize of the hole that you're trying to make. And that's assuming that the pipe itself is just going to shatter and move out of the way. And where you can run into problems with that is if you've got the ductile type pipes, the steels and the ductile iron, they don't tend to shatter. So there are limitations when you're dealing with that. The photograph on the bottom here is a project that was done recently in British Columbia, and it went from 350 millimeters of 14-inch up to 900 millimeters of 36-inch. So it was a 650% increase. That is conditioned on the ability of the ground above the pipe to take that energy and to take that compaction. If the ground cannot take the compaction, then you can't do that much upsizing. And here's a slide we've developed in the last number of weeks. So what I'm trying to describe here on the picture on the left is what actually happens. For starters, let me premise that we all know that geotechnical or soils are very varied. All bets are off. You have to be very conservative looking at soils because it changes drastically as going through a trench. But we can make some assumptions, and this is a fairly good assumption of what happens. We have found, if I look at this slide here in the picture on the left, my existing pipe is the blue pipe on the bottom. The new pipe I'm putting in is the green pipe. We have found in 25, 30 years of pipe bursting that very, very rarely do we not have inverts matching. In other words, the crown of the pipe is generally what moves. So therefore, the compaction happens above the crown of the pipe. If you go back and you look at the trenches that were done, Murphy Pipelines puts them on quite often, you'll see guys digging trenches back in 1900s and 1920. None of that material was backfilled. Therefore, the material that was put back in the hole or the trench on top of the pipe, I'm saying would have probably compaction of maybe 80%, 80, 85% maximum. So therefore, it has an ability to absorb compaction, whereas the existing ground would have had a much higher density. Then on the left-hand side of that picture, you see that X and 10X. A number that came out of a study by Ray Sterling back in 2009 approximated and said it's about a 10-to-1 compaction ratio. In other words, if I'm expanding 100 millimeters on the pipe size, I will affect the ground around me to about a meter around. From an engineering point of view, anything within at least that meter needs to be very carefully analyzed. In other words, cross utilities need to be very carefully analyzed as to whether it is suitable to be displaced or whether it's suitable to have this pressure put on it. If it's a 300 millimeter AC water main, I would be very reluctant to do it, or I would air gap it to make sure that we don't have any effect from the bursting happening on that AC main. If it's a 750 concrete pipe and it's up towards the top of that, yeah, I'd be less cautious about it. But that's essentially what happens. And you will see as well that the effect of the bursting only goes about 10 times up. Thus, if I'm 4 or 5 meters down, you'll probably find that the compaction only radiates up from the bursting zone, depending on the upsize we're doing, but maybe 2 meters, meter and a half, 2 meters. And the rest of the ground is just unaffected by this. So the materials that we can burst, well, the original backfill is what I'm really talking about, the original backfill on top of the trench. And that, as I said, is not very well compacted. Expandable clays and then loose cobbles and running sand. That major upsize in the previous slide, that was river materials. So it was gravels and sands from a river. That's what we were dealing with. So it did have the ability to absorb that 650% increase in upsizing from the pipe. If you're down into sandstone and you've got a narrow trench that was just dug by hand, that was just bigger than the blue pipe, you're going to have a very difficult job in trying to pipe burst that. And we have found in extreme cases whereby, if you go back to the 1910s, where they would have dug a pit 3-4 meters long, tunneled, next 3 or 4 meters into the next pit, and rather than digging the whole trench out, 3-4 meters deep. It's just an easier way of doing it at the time. So if you've got that, you've got a tunnel, then you're quite limited on your pipe bursting. When we pipe burst, and it doesn't matter whether it's pneumatic or static, you are using energy to do 3 things. You're using energy to break apart the old pipe. You're using energy to displace the soil that we just talked about now. And then you're using energy to pull the new pipe in through the hole that you've made by the cone when you've displaced the soil. Depending on the soils and depending on its ability to move back around the pipe and adhere to the pipe and cause friction, you may or may not want to add lubricants in there to try and isolate the pipe, the new pipe, from the surrounding soils and allow that pipe to slide through. You cannot do much about the energy that you need to break apart the existing pipe, or you can, and I'll talk about that in a few minutes, but you can't do much about the soil that you're doing, but you can do something about the lubrication and the friction on the existing pipe behind. So lubrication is a good example. Now, generally on the smaller bursts, the 200 millimeters, even up to 300 millimeters, you generally have enough horsepower to pull through. It's when you start going 400, 500, 600, 900 millimeters, that's when you really need to watch how you use your horsepower or your power, your pulling power, and try and lessen any areas that you can lessen to allow you to have maximum energy to both break apart the existing pipe and to pull in the new pipe, to make the hole in the ground for the new pipe to come through. So I'm still on general pipe bursting. I haven't deviated off into the pneumatic versus static yet. So this is the general head layout. What we've got here is we've got the bursting head, and you can see it's steel cones. In this case, it's a static system. If there's a pneumatic system, there'd be a hammer inside that hammering. I just talked about the energy to break apart the existing pipe. Here you can see the cutting blades on the top of that are over kind of on 1 o'clock. If you're looking at it from behind and looking up towards the front, cutting blades are at 1 o'clock. So by putting a cutting blade on there, you are cutting the existing pipe. Therefore, you're hopefully using less energy like that to cut the pipe and get it out of the way. And therefore, you're using most of the energy to open the hole up. I've also circled in there too a hole so that where the lubricant comes out. So that lubricant comes out just behind the head and will hopefully lubricate that whole the new black pipe that's there and lower your friction on that. Now we're going to get into the pneumatic process. Both processes are quite common. We tend to find that the pneumatic process is more common in the southern US, static and kind of California, and then we get the static system is more common as we come north in the US and into Canada. So the pneumatic system is a hammer. I'll give you an example of this. TT Technologies has a tool called a Hercules. It generally can burst up to, say, 250 millimeter pipe. It's just a regular working tool because the vast majority of pipe that we're dealing with is 200, 300 millimeters, 250, that kind of size, which is 8, 10, 12 inch. That tool is, I'm going to guess, at about 400 kilograms, 800 pounds, 900 pounds. There's a hammer in there that is about 150 pounds or 75 kilograms. It goes back and forth at about 70 strokes per minute. When it hits the front, it's steel on steel. So there's a very sharp smack when it hits the front. Then as it comes back, the air channels are set up so the air slows the hammer down as it's coming back, and then it hits a rubber cushion on the back. Therefore, the net result is that the forward action of that hammer is, depending on the soil, I'm just going to say the net action of that hammer is, say, 75 mils forward, 25 mils back. And so the air coming out of that compressor on the right-hand side powers that hammer to move back and forth at over a beat per second and move forward and break apart the existing pipe and push the soil out of the way. Then on the left-hand side, you've got a winch, which has got a cable on there, and that cable is providing some tensile forces to keep the thing on line. It's really not pulling it in place, it's just keeping it in line. The one issue with this picture that I always have is that black pipe that's coming out of the screen towards you, that is within that 10-to-1 zone. That black pipe is an example of what should be isolated, or it's a heavy-duty, high-density polyethylene pipe that was bursting a number of years ago, and somebody's just taken decisions that it's fine, don't worry about it. So the pneumatic process, so we go back and we've got the winch. It provides constant tension, as I said. So it's what we call a twin capstan winch. It's not a geared winch. A geared winch, because the hammer action will slow down and speed up depending on the soil there. So it can slow down and completely stop for a while and just hammer away trying to displace soil. If that was a mechanical type coupling onto a winch, you'd stall the winch out, which is not a good idea. So it's a twin capstan thing that will allow slip depending on the tonnage you put on there. The winches out of supply, they've got 5, 10, and 20-ton winches. A 10-ton winch is what you'd normally use, up to, say, 300, 350 millimeter pipe. Above that, with the tools above that, you're going into a 20-ton winch. Lengths of run, well, if it's a sewer system, generally your manholes are spaced about what used to be 450 feet apart, maximum, or 150 meters apart. That's still the case, and that's a general run for a sewer line. Pipe bursting, in similarity to pipe ramming and pipe jacking, you only have a gap outside the pipe of, say, 25 millimeters. Therefore, you're limited as to the lengths you can go. Once you go about 100, 150 meters, the material starts to come back in around the pipe and your friction starts to go up. Whereas, a little bit off the topic, but directional drilling, you make a hole about 150% of the size of the pipe. That's why you can go 4 or 5 kilometers with directional drill, because the hole is much bigger. So you don't build your friction up as fast. But just a little side issue. In water mains, again, you're limited because you're pulling the pipe in. As I said, you've only got a gap about 25 millimeters bigger than the pipe. Therefore, the maximum you can pull in, again, is about 150, maybe 200 meters. Again, it depends on the soil. If you've got a soil that's cohesive, you push it out of the way, it stays in place with a hole opened for hours, then you can pull the pipe as long as you want. However, if there's no cohesion in the soil and tends to move back in around the pipe, then you could be limited at 70 or 80 meters. But again, you don't want to start going through valves and fittings and stuff like that. And I'll show you pictures afterwards of the mess that you can have when you try and pipe burst through unknown valves or unknown repairs. Pre-video, very important in pre-video, especially in sewers. If you have live sewer locations, you want to make sure you pick up the live sewer locations. In pipe bursting, we are able to burst through and not pick up a sewer connection, but you'll find it within weeks or months. That will either back up or percolate up to the ground. Existing sags, I often get asked, will pipe bursting fix existing sags? It will fix a displaced joint. It may tend to lessen a sag, but it won't fix the sag. But what you will find is, because your either N value or your C value, depending on its pressure pipe or a gravity pipe, it will drop substantially because you're going to high-density polyethylene. You may find that the sag is no longer an issue because it's just going through there as a siphon. But you can use that and or come back afterwards and fix the sag if they still exist. Fittings and on valves and fittings on water mains, I'll show you that. I'll show you what happens when you don't do that. And communication. Again, just looking at the pneumatic system, you see the same issue again, the same pipe bursting tool coming through. And that's, I'm going to call that a smart head in here because that's a pneumatic tool. Here we've got examples of pneumatic tools. I must say PW Trenchless hasn't used a pneumatic tool in probably 15 years. But these are old pictures that I dragged out. So you've got the picture here. This one, I hope you can see my mouse. So the picture on the left, you can see the tool as it's coming towards you. It's got a rear expander on there, and it's got, on the very front end, it's got cutting edges that will break apart the existing pipe. Back to what I talked about earlier when I talked about condition 1, 2, and 3. This is only to alleviate condition 2. The existing pipe here was a PVC pipe. It was in great shape, but it had no longer got the capacity because they were densifying this area, putting in high rises, replacing what were single-story buildings with high rises, and the sewage flow is increasing quite a bit. I talked about the lengths of pipe bursting. Pipe bursting, like most trenchless technologies, is more feasible and more cost-effective when you can make longer lengths. Because your entrance pit and your exit pit are fixed, they're fixed costs, the longer that the length that you can burst from pit to pit, the more cost-effective they become. Same as on CIPP, same as on slip lining. Therefore, if I've got a run of, say, 20 or 30 meters between manholes, it's not very cost-effective to do the 2 pits. But in lots of cases, if it's a straight run with a manhole, I can burst right through the manhole. And that brings back my cost effectiveness again. The third picture over is the other end of the pipe. Here you can see on the right-hand side, you've got the beige compressor, you've got an air line going through, and you can see the air exhausting out through the back of this pipe here. It's a very loud process, and in this case, we were in the middle of high rises, and it was echoing everywhere. But it was a very, very loud process. On the right-hand side, the last picture, when I talked about lubrication, I talked about the lubrication because what you were trying to do is to stop the material, the sands, after you've burst and opened up the hole, it tends to collapse back in on the top of the pipe again, and your friction on the pipe builds up. Therefore, you lubricate to try and lessen that friction. An additional way of doing that was to put another bursting head on the back and be pushing from the back. A little bit like a locomotive on the back of a goods train, pushing on the back as well as pulling on the front. Same concept. Here we're looking at a rear expander again. This is an interesting one. This is the first time we used that rear expander. This happened the day after 9/11. So I was hoping to get the technician from the supplier of the equipment up to help us make sure we had everything right. And he was stuck at the border. I always remember this day. That pneumatic hard tools, you can burst from 95 millimeters, so it's 3.5 inches all the way to 24 inches or 600 millimeters in diameter. And then new pipes, anywhere from up to 1,500 will be pushing it. Probably 1,200 is probably the biggest we would want to get into. Front expanders. Front expanders are systems the expanders on the front of the pneumatic tool rather than the back of the pneumatic tool. The big advantage is that in a front expander, you can burst into an existing manhole, take off the cone, and then reverse the tool back out the pipe. The disadvantage is that the tool itself is quite small because it has to fit through the pipe, and therefore your energy is not that great. But in certain circumstances, it works very, very well. Here we're looking at a condition 1 and 2. So in this case, the pipe was starting to fail, that concrete pipe, because of sewage was starting to fail with hydrogen sulfide. Static pipe bursting. Static pipe bursting, like pneumatic pipe bursting, is just a way of breaking apart the pipe. So the top picture that you're looking at is we're feeding rods through. When we discussed the pneumatic system, we used a cable. The cable was only to keep the tool on line and in the pipe. It didn't really provide any pulling force to break apart the pipe. All of the energy to break the existing pipe and to open up the hole in the ground was provided by the pneumatic tool. In static bursting, the cone on the front of the pipe is just a dumb cone. It's just a steel cone, and in the shape of a cone, it has no energy. It cannot produce any energy. All of the energy to break apart the pipe and to open the hole up has to come from these rods. So they use a rod system. A cable system would not be strong enough. A cable would stretch too much. As I said, on the pneumatic system, again, you're 10 tons, maybe 20 tons. This one here, you're pulling at about 80 tons. So a big difference in pressure. And 80 tons is for your 200 millimeter, maybe up to 300 millimeters diameter pipe, so 12-inch pipe. You're limiting out with an 80-ton machine on a 300 millimeter pipe. So you're feeding the rods in at the top, and the second picture is you're getting ready to pull the pipe back in. And if you look carefully at the front of that, there's actually a cutter in there. The cutter is it's like a pizza wheel cutter, and that is what you would tend to use on pipes that have ductility in them. And then behind that you've got the comb, which opens the dirt up, and then you pull your new pipe in. So the key points of static are it's just a straight pull system. The head is dumb. It has no ability to do anything. But they're all hydraulically operated. You have this roller cutting split blade system on there, which will cut the pipe out of the way. And it's a quick rod system. In other words, you're not screwing and unscrewing rods. It just makes it faster. Just couples together. The one thing I will say about static systems is much easier. You don't have a compressor. You don't have air hoses. You don't have a starter valve. You don't have a pneumatic tool that you're trying to get a hammer going, all that kind of stuff. So it is easier setup. The other thing I spoke about a few minutes ago was with the lubricant, is that the material moving back and around. If you are underwater, in other words, you're below the water table, because the pneumatic system tends to go forward 75 and then back 20 and forward, back and forth, it tends to vibrate the soil around it. And of course, that causes your cohesion in the soil to be broken, and the soil moves back in around the pipe much more easily. So if you're below the water table, you tend to bring the soil back around the new pipe much more quickly, and therefore you build up your friction much faster. Static system doesn't tend to do that. It tends to open the hole up, and that hole stays open much longer. As I've already said, static tends to be more common in northern US and Canada for some reason. Don't know why. Here's pictures of your static system. You can see there on that picture on the left, the head is just a dumb head, just a cone in there. It's got the rod sticking out. You will see here what's happening too is that in this case, it's the city of New Westminster here in British Columbia. They have a lot of old clay pipes that were put in the 1900s, which have but they have failed longitudinally. So they've failed along the spring lines. And then it's not a big movement from there for them to move laterally, and then you've got a failure in there. So these pipes have failed, and that's why I'm saying it is 1 and 3. So 1 is that they're leaking, and they've got a lot of I&I, and 3, structurally they've failed. Those conditions could be solved as well with CIPP. They didn't have to burst that, but the cost effectiveness of CIPP versus pipe bursting, depending on the runs and depending on the contractors and so on, it's not that different. It can be 10–15%. But you can see the effectiveness of trenchless as well. They pit on both sides. There is only 3–4 meters long, and then you're going to have another same pit at the other end, 3–4 meters long, and you're going to be able to effect a 100-meter run of pipe and change it overnight. And then you're going to have your lateral connections coming in. An average lateral connection, you'll see later on in the video, is only the size of the hood of a pickup truck, so not very big at all. Here are 3 or 4 different pictures of static bursting. So on the left-hand side, you've got a large bursting head. You can see the person on the right-hand side, that cutting wheel, and in fact, really demonstrates the cutting wheel in the second slide. So it's splitting ductile iron pipe. You can see the wheel sticking up out of the pipe as it's splitting apart the ductile pipe. You will also notice on the ductile pipe that it is not breaking into shards and pushing out of the way. What it's doing there is it's cutting the top of the pipe, and then the pipe is kind of failing at about 9 and 3, and that's moving out of the way. But what's staying there is from 3 down through 6 and back up to 9 o'clock. That pipe is not failing. So you have to be aware of that when you're bursting pipe, particularly ductile iron pipe. You're very limited on the upsizing you can do on it. The recommendation generally is 1 size up. Other than that, you will tend to affect the new pipe that you're pulling in. In that one, I'm talking about conditions one and two. So obviously in that one, they had leaks in that ductile iron pipe. Well, that's actually a demo. But if you have leaks in the pipe and you're undersized, then you would burst. On the one on the left, it was a large upsize. In that case, the existing pipe was in great shape, but it was too small. So therefore, that's a condition two that I talk about. Then when I go to the next one, the one that says pipe bursting in frozen ground in Richmond, BC, that one actually was a pipe failure. That was fiberglass pipe. It was 4 or 5 meters deep in Richmond, British Columbia, which is the water table is down about a meter and a half. So we were about 3 meters below the water table. And we had a block building, 20 meters high, cold storage building, 20 meters high, within about 15 meters of this pipe. So there was no way we could use well pointing. If we used well pointing, our drawdown curves would have gone under that building, and we'd have had failures in that building. So we chose to freeze the ground, which means that your pits, it's just very limited to the pit itself where the ground freezing is, and allowed us to get down there to replace that pipe. On the right-hand side, that was a 900 millimeter, 36-inch corrugated steel pipe that had failed because it was getting saltwater ingress twice a day. It had failed that way, and they couldn't fix it. There was also those silos, if you can see in the top right-hand side, there were silos right on top of the pipes, which are silos without piles under them, so they were sitting right there. So the only way they could replace that pipe was using pipe bursting. And again, it had failed, and we were upsizing a little bit because we put in a 1050 or a 42-inch pipe in there. So I'm going to talk about the risks involved with pipe bursting. Pipe bursting is one solution in one of many, many solutions in trenchless technologies. And it solves the problem, as I said, in that when our capacity is too small, or we've got a failure in the pipe, that's what it solves. If you've just got a leak in the pipe, or you've got a cracking in the pipe, CIPP is a better option in there. So it does solve one problem. You're identifying that problem, of course, with the video beforehand. You've got to watch for your connections. And a lot of times, the reason you're upsizing a pipe is that because we're densifying a neighborhood. Well, if we're densifying a neighborhood and we've already had 20 residential houses on that street, and we're now abandoning those, we're putting in multifamily, we're putting in high-rise, we've now generally got one connection out of a multifamily complex or a high-rise complex. Therefore, all of the 20 houses that existed have had 20 connections coming into that pipe. We don't want to reconnect those 20 connections. Invariably, the connections that were not severed at the main, they were severed back at the property line. So you have to generally go in with a lamp camera and verify that those connections are abandoned, because they look still live, because they will have some groundwater coming through. So you need to verify what's happening. Peripheral utilities, know what's below. We have to know what's below, because we are disturbing the ground. As I said, that rule of thumb, the 10 to 1, it's not a bad guide. And there's also that paper by Ray Sterling. That's a very good paper that was done by Ray for the US Corps of Engineers. It comes up quite often because a lot of people will ask, oh my goodness, what happens if you're going to pipe burst here? I've got a water main 4 meters away. What's going to happen to my water main? Well, you can get a very good idea from that paper by Ray what will happen to that water main, if anything, because there is ground movement, but what effect has the ground movement got, and what effect will it have on surrounding utilities? Here's what happens when you don't go and do the video. This is the water main. You can see on the picture on the right-hand side, that was an abandoned valve and a pipe repair that happened who knows when on a water main. Remember, most of the time when you're repairing or replacing a water main, it is because you've already had a number of breaks in that water main, and you finally just lose patience and say, okay, forget it, we're going to replace this whole water main. We've had enough breaks. This is stupid. We've got to replace this whole water main. But when you do that, invariably, you will have had repairs in there. So even if the main material of that water main was, say, asbestos cement or steel, the repairs that would have gone on there, they wouldn't have used steel, they would have used a different product. We need to know what that product is, because if we're trying to cut the existing pipe, we will use certain tools to cut that pipe. If the material changes, we will use different types of cutters. Number one. Number two, we're depending on the longitudinal strength of the existing pipe to essentially stand there while we put a blade against it and cut it. If we're coming into a coupling, like a row bar coupling, the strength of the row bar coupling is far higher than is the hoop strength of a row bar coupling is far higher than the longitudinal strength of the pipe behind it. So what we'll tend to do is we can tend to crumple the pipe, especially like that pipe on the left-hand side. That's a particularly bad one. That was some steel piping that was manufactured just after the Second World War. Very, very thin-walled. It was perfect in hoop strength, but longitudinal strength was very, very weak. So the owner's responsibility and the contractor's responsibility, these are just kind of basic guidelines. If one does that NASTT course or similar pipe bursting courses, the 2-day-long courses, you will find out an awful lot more on what needs to be looked at from an owner's point of view and the contractor's point of view to either to present a good contract and then to get reasonable and accurate pricing back in from the contractors. So number one, as I said, the material, the pipe type you just saw on the previous slide, when we didn't know that the repairs were in there, that's what can happen. You can get into a mess. Bypass pumping in sanitary sewers, very, very common. Bypass pumping, it helps for the owner to have a very good idea of what is required to bypass. Otherwise, the contractor has to assume the worst. So they make some calculations based on the diameter of the pipe and what's the maximum that can flow through there, versus the actual flow through there might only be half or a third of that. You don't need to overpay for bypass pumping. The legal issues, well, I'll show you later on. We do a video where we're actually bursting through the backs of people's yards through easements that, yes, legally existed, but mentally all the homeowners had totally forgotten about. And so it is beneficial for the city to go in ahead of time to the owners of the houses and explain to them, there is an easement in here. We're just replacing your sewer system. This is what's going to happen. If you let us to the contractor, it's just too late at that point. Contractor responsibility, well, obviously to have their crew qualified. I'm going to say the crossing and the adjacent utilities, that can be provided, that should be provided by the owner, but the contractor should verify it as well, because it may not be, it may come from the owner's papers alone as to what they've got, but there could be other utilities that have gas pipelines or electrical conduits in there that the owner may not be aware of, but the contractor should be going out to all different possible owners of utilities to verify what's in there. Again, because that's where it gets affected in that 10-to-1 rule. Correction of drop joints, well, that will happen in bursting, but as I said, the line sags may not happen. And the service location, well, again, whether the connections are live or not, that should be the contractor. And that's not just a lamp camera. You would look at a lamp camera, you'd look at the area, you've got 3 or 4 different criteria to see if the viability of connection. This is just a brief idea of some of the submissions to be submitted from the contractor. The methods of bursting, it's good that the owner sees what the contractor is proposing to use. If the contractor is coming back and they're proposing to use pneumatics and you're 3 meters below the water table, I know it's the contractor's responsibility, but it will tell you their knowledge and their expertise. And that, again, the type of tool. Again, if they're trying to do a 16-inch or 400-millimeter pipe burst with an 80-ton pipe bursting machine, you can certainly question their ability to do the work. And I would recommend that you do not just go out for tender with these things, but you go out for an RFQ, and so that gives you the ability as the owner to question the contractor before you make an award. The type of lubricants, The MSDS on the lubricants, they are putting these lubricants into the soil. You as the owner want to know what's going into your soil. You want to know if there are issues with them from an environmental point of view or not. And again, the proposed runs. You're also, by asking these questions, you're forcing the contractor to think. So you're making sure that the guy is just not going in blind to do it. The contract plans, again, the lengths of each burst. You don't want to have on your contract drawings a burst of 300 meters. It's just not going to happen. You need to know that the bursts are going to happen in 120, 140 meter lengths maximum. Again, the construction easements, that's back to the legal side of things again, bypass system, the layout. The bypass system, there's liability from the contractor. There's also liability from the owner about bypass systems. You certainly don't want a major spillage. And then your exit pits. So we're into case studies. We're into the last 3 or 4 slides, folks. This was a condition 2. So the pipe was too small. There is foreshortening on this photograph, so it does exaggerate the new pipe going in. But you can see this is a major upsize. That existing PVC pipe was a 350 pipe, and the new one going in is the 900 millimeter pipe. And if you look at the very front of the bursting head, you will see those cutting wheels on there. So that cutting system is set up so that it doesn't allow essentially the PVC pipe to get away. It holds it in place with a mandrel on the inside to maintain its roundness, and then hits it with the cutting wheel to split it apart. Then the other thing that's unique about this layout that's here is that the material, because it had a high water content, we essentially hit it with the first cone, moved the material out of the way from, say, 450 to about 600, and then we let the soil relax and essentially let the pore pressures come back into the soil around the pipe again and lower your friction. But that's where the barrel section is. Then hit it again with a cone, move the soil out of the way to about 650, 700 millimeters in diameter. Again, let it relax with the second barrel section, and then hit it with the last cone to move it out of the way to about 1050 in diameter, and then added the lubricant in it to bring your black pipe in, which is the new pipe coming in. Alison, the next one here is a pipe burst. And let me just introduce this first. This is a video that was produced by the city of Nanaimo on Vancouver Island, and it was dealing with the sewer up the backs of the properties. Let me just say, very common issue in Western Canada. Cities would have come in and put a street in, put a water main in, and on the street, and then the people would have had their own septic field in the back of the house. Then 1950s would have come along, they go, oh my goodness, we better pick up all those septic fields because they're not working too well. They would have gone and put a sewer system in, and this is the only place for the sewer system would have been right up the back property line. Now, 50, 70 years later, we're in the position we've got to replace those sewer systems because they're now too small. So we've got to go back in and replace those sewer systems. And in that case, it was 150 millimeter sewer, 6-inch pipe. We're replacing with an 8-inch pipe. And this is a video of what's happening there and the effect of what's happening in the surrounding area. Alison?
Trenchless technology is a rapidly growing sector of the construction industry and includes different methods to replace underground utilities that require fewer excavations and no continuous open trenches. Pipe bursting is one trenchless method where hydraulic force is used to split the old pipe from the inside, while a new replacement pipe is pulled in behind. Pipe bursting was used to upgrade a backyard sanitary sewer along Vancouver Avenue. The existing 150mm diameter concrete sewer was installed in 1959 and runs along the rear of the properties, seen here where the orange safety fencing is installed around each property connection to the sewer. Given the access challenges, mature vegetation, and proximity of existing structures, the impact of the traditional method of digging up the entire sewer was not preferred. The existing pipe material and soil conditions were evaluated and both supported the use of the pipe bursting process to replace the old sewer line. The new sewer line is a continuous piece of 200mm diameter high-density polyethylene pipe, approximately 215 meters in length. This is laid out along the roadway and set up for pullback using vehicles and other stationary objects to provide the appropriate bending radius and grade of the pipe at the upstream entry point. This is one of the few excavations that does require some space and is set up to accept the new pipe so it can be monitored during the process while it is pulled back into place. This process only requires that services to each property be excavated, including the entry and exit pit. The service pits are excavated prior to pipe bursting, and temporary connections are installed to protect the private side service from any damage. Once the new pipe is pulled through, the services are reconnected and excavations backfilled. On Vancouver Avenue, the entire section of sewer was installed in just one day, with the project taking only 10 working days to complete from start to finish.
So this is the impact just a few hours after the burst. So you can see we've made the connections. That's the size of the connection from each house. As I said, about the size of the hood of the car, hooked onto the pipe. And that's the after effect. In fact, that one there, they replaced the connection right up to the house for those homeowners because it was failing. It was ready for sod. Here was a manhole that was existing halfway through. So we were able to burst right through that manhole and then grout it in afterwards. One of the big benefits of pipe bursting, like CIPP, and a lot of these other rehabilitation processes, is that manhole, in my opinion, is in great shape. It has another 100 years of life in it quite easily. If we were to open cut that, we'd have abandoned that manhole and backfilled it or just pulled it out of the ground. But that's just a waste of resources. By using pipe bursting and or CRPP, any of the trenchless rehabilitation processes, we can utilize I'm getting a message, lost network.
You should be back.
Hi, everybody. I think David's having some technical difficulties on his end, so we're just at the end. I'm hoping that he jumps back on soon. We're trying to figure out what his problems are. I've seen a lot of questions come in, and that is just fabulous. A lot of these are really good questions. While we're waiting for David, I realize I didn't introduce myself. My name is Caroline Amyot, and I work for the City of Waterloo as a senior project engineer, and I mostly manage capital works projects. So I find this topic very interesting in terms of having to manage. Often we're doing rehabilitations and trying to find solutions to fix some of our old infrastructure problems. It's not all building new. So I'm seeing there's a bunch of questions from municipalities as well. So I'm guessing that resonates with you as well in terms of finding other tools in the toolbox to use. So yeah, we'll see here.
Carolyn, we can play his second video.
Okay.
If we want to do that. I'll go ahead and do that. Awesome.
Okay, so we're going to show the next video from his...
This is a project in CUIIC, just east of Vancouver, up against the mountains. This is the upsizing of an existing 300mm pipe that is being upsized to 450 millimeters. It's a trunk line that serves a lot of development is going on in this area. This pipe is there's three runs in this contract, about 500 meters in total. This is the first run going in. It's bursting uphill. This is the entrance pit here. Pipe is entering here, going under that tree, past the vac truck, and bursting uphill, up through underneath all that grass. To have open cut this would have meant the removal of all of those trees, and it made a right mess in their garden. In the meantime, it's going up to this pit up here where the tugging unit is. So the tugging unit is here. It's a rod system. It pulls a bursting head through the existing PVC pipe with the new pipe attached onto the back of it. You can see the stub of the green pipe underneath you there. That's the stub of the existing pipe that's going to remain and be hooked up into the black poly pipe when we're finished. Just going to turn around here and go back down and have a look at this job again. So we're heading back down. Again, all those trees would have to be removed if we were open cutting this job. As we go down here, we see this vacuum truck. This vacuum truck is picking up the flow coming out of that apartment building on the right hand side. This has to be done when you're doing the actual burst, because of course your pipe is disconnected at that point and bypassed. The black pipe, the smaller black pipe that you see going through here, is actually a bypass pipe, because you have to bypass these runs while we're working on the main trunk. This pit here would act as an entrance pit for the next burst going through the other direction as well. So one pit will act both ways. And then as we come up here, we look at the area with the steel plates. That's where the sewer connection is from the other building. Those plates will be removed, and we'll have the vac truck there when we're doing the next burst. That next burst will go underneath these oak trees, through that garden, and up into that pit right there. Then the third burst will go from that pit all the way through that pathway and off into the distance, about 120 meters. So these three bursts make up about 450-500 meters in total.
Okay, I think David's back. We're just having trouble hearing him. So thanks you for your patience. We're working behind the scenes here. Hopefully we get David back here shortly.
There he is.
Sorry,
Hi,
guys.
David.
Sorry, guys.
All good. We're on slide 35, David.
Which is the, okay.
The PVC pipe is shattered and the upsize happening.
Yep, exactly. One, that's that third or fourth slide that we had when I talked to materials that burst, some burst and some are ductile. You can see that PVC is kind of a hybrid system. It will tend to shatter and burst like pieces of concrete or asbestos cement moving to the surrounding grounds. but sometimes it doesn't. It's got some ductility in it. And it's a function of the age of the pipe and its ability to sometimes it'll break and sometimes it doesn't. So you can see on that slide on the left, you see that the plastic is breaking apart. On this picture on the right, again, you see that cutting head there right in front of the guy. It's got that wheel on there. He's got his hand on that cutting wheel. So that cutting wheel is putting a point load on the plastic pipe or the steel pipe. It's cutting it, moving it out of the way, and then the cone coming in behind is where the energy is really being expended to open the hole up in the ground, and then you're pulling your pipe in. And that is it. I'm ready for questions. I apologize for the technical difficulties. I hope you got some good technical information, but the computer side was not great, but whatever.
Oh, sorry. Now I'm up. I'm on. Thank you very much, David. That was great. That was a lot of good information. We did have some questions come in, so I'll get right to those. The first question comes from Mike DeTharet from Acrestone Consulting. He asks, when bursting a pipe, the head uses brute force to break the old pipe and push around the soil to make room for the new one. A, is there a limit to the ratio between the diameter of the new pipe and the diameter of the old pipe? And B, how is that ratio affected by the nature of the ground? Now, I think you answered this in the question. These came up during the presentation, but I think some of these aren't a bad refresher. And to me, that's a very important thing to make sure that we get straight when you consider pipe bursting.
I would preface the answer in that you're dealing with disturbed ground. So therefore, we don't know the level of compaction that was achieved on backfilling that ground. But we have to assume that the level of compaction was not what the virgin ground would have been. So in other words, the trench, or the ground outside the trench, would generally have more compaction than the trench itself. The trench itself, depending on the age when the pipe was put in, will either have no compaction, so it'll just be naturally, or it'll have some compaction. But even nowadays, I think if you go out and look at any operation with an open cut situation, no contractor is going to put material in on top of the pipe and hole pack a foot over the top of a brand new pipe and expect it to stay round. You would tend to make it oval. So therefore, most contractors that I see put a meter and a half. It's a deeper trench. They put a meter and a half of material before they do the first hole pack. And as we know, that hole pack will only go down 300 or foot into the material. So therefore, we have to assume that about a meter of material over the top of the pipe has little to no compaction. So Mike, that's where your expansion is going to go. If that answers your question.
So Alison, I'm not sure if there's the ability, I guess you can just type your question back in if you have sort of follow-up questions to these questions, and I'll just watch them. I do think the first question, where is there a limit to the ratio between the diameter of the new pipe and the diameter of the old one?
It's a soils function, Carla. It's totally dependent on the soils. If you were in sandstone with a very narrow trench, then you might be limited to just size on size, or maybe one size up. If the trench was bigger than the pipe by, say, 2 or 3 times, if it was a modern trench that was, say, a meter wide or meter and a half wide, and you were talking about a 200 millimeter and 8-inch pipe, then you've got a lot of room. If it was an old trench hand dug that was 50 millimeters or 30 millimeters bigger than the outside diameter of the pipe in sandstone, then you really don't have an awful lot of room to move.
Okay, hopefully that answered the question. If you have more questions, follow up, just let them come in. I am watching here. I think the answer is it really depends on how deep, what the conditions are, like a lot of factors. It's not just there's no one straight answer.
No,
how often do they, just on that note, if you want to pipe or something, go and do geotech information? Is there any value in that?
yes, there is, but one of the issues is that no testing company or no boring company is ever going to go right on top of the existing pipe, because they're totally adverse to doing that. So therefore they go 3-4 meters over, and that information is not of any use to us. So I would strongly recommend, if you're intent on pipe bursting, have a vacuum company go in and do a vacuum excavation down to the top of the pipe, rather than using an auger or a drill bit to go down, and then try and do tests on that. Only if you were looking at a large upsize and a large pipe would I look at that. And really what you're trying to do then is you vac down, say you're going down a meter and a half above the pipe, and then you're going down and doing a compaction test on that material to see if my hypothesis is my theory is right, that the compaction of the material over the crown of the pipe is only at 75-80% compaction. That will tell you then whether you've got the ability to compact. That material has the ability to compact from the tools coming through, and you have the ability to pull the pipe through. But if you're looking at, say, something that's 400, 500, 600 millimeters in diameter, would I go to that depth of analysis beforehand?
Right. Okay, that's great. Okay, so the next question, how far is the impact horizontally? This is from Ahmed El-Fadili from Hatch.
It will transmit. It will transmit as a shock wave, radially. I'm not an expert in that. I would refer back to Ray Sterling's analysis, but it will transmit radially around there. It all depends on the material that has the ability to absorb that shock versus the ability that doesn't have the virgin ground essentially doesn't have the ability to compact, so it won't compact. So therefore all your compaction will tend to go up. However, if I was in a peat bog and the original pipe had been put in a peat bog with say compacted material above it, then the compaction will go down, out and down. But that's a very rare situation.
Okay, great. Okay, next question. Kevin Zhang from the city of Burnaby. What limits the max length of a run for water pipe? Is it the length of the winch, or what is it that, because you don't have manholes for water main, right? It would be.
Yeah, no. Kevin, we've done work in New Westminster just down from you, below you, where we've pipe burst 100 meters of pipe, taken off the tool, and the pipe will move in the hole with a backhoe. In other words, with 3 or 4 tons. So effectively, at that point, there is really no limit, except maybe the number of rods we have in our machine, which is about 180 meters. But generally, in 180 meters, you're going to have some valving. You're going to either have a hydrant valve, a hydrant T, or you're going to have an intersection, or you're going to have a repair. And those will dictate where you're going to do an entrance and exit pit, or at least where you will do an excavation. If it's just a T for a hydrant, you might just do an excavation, cut the T ahead of time, and then burst right through it. You got to go down there anyway to put a new T on for the hydrant, so it doesn't really matter. So I would say, you could get it. It depends on the ground. If the ground will stay open, if it's cohesive, and you move it out of the way and it stays in position, then there's really no limit. If it's in a wet ground where you've got lack of cohesion on the soils, it'll move in around the pipe fairly fast, and you're probably limited to 60, 80 meters, 100 meters.
Okay. Okay, next question. Hopefully that answered the question. This is from Kevin again. What is the size requirement of the insertion pit?
The insertion pit would be, say 16, so 50, a 5 meter long cage with a tail coming out of that, with a ramp coming out of the back of that. Again, it depends on the depth. If I'm down 5 meters, then that entrance ramp is going to be coming up at 45 degrees from the back of that cage. And again, if if I'm bursting a 200 millimeter pipe is one thing because it'll be deflecting. If I'm bursting a 600 millimeter pipe, then you need a longer cage. You might need you might need 10 meters, a 10 meter long cage. The exit pit tends to be shorter because that's where the pulling system is. That just needs to be that pulling system plus a couple of meters. And that pulling system is 3 meters long plus a couple of meters, so 5 meters long. So the exit pit is 5 meters long. The entrance pit can be 5 meters long plus a ramp.
Okay, so the minimum is sort of 5 meters for the entry and 3 meters for the exit, but then it could be bigger depending how deep you need to go.
Yeah, and you could do it tight. You could go 3 meters if you're just doing a 150 millimeter pipe. If it was really a condition that you had to keep it very tight because of existing ducts crossing in the way, you could keep it tighter for smaller pipes.
So average. Okay, that's great. Okay, this is from David Lee Yee from the town of Sylvan Lake. This is a good question. Can we pipe burst small diameter cast or ductile iron water mains? And there's sort of, this is another one, bends, repair clamps, and or fittings. And depending on your answer, I might want to ask something too.
Okay. You can't burst around a bend. If you've got, think of the bursting system. Think of cutting cheese. If you're cutting cheese with a wire, the wire will tend to straighten out. If you're cutting around bends, the bursting head, and whether pneumatic or static, will tend to straighten out. Therefore, it'll go outside the path of the pipe, which is what you do not want. If it's a very gradual bend with slightly pulled joints, you possibly can do it.
Okay, so in water main, yeah, you have your sort of 11 1/4, and then your, they go up.
You cannot pull through a manufactured bend.
Okay.
So that would be back to, Caroline, that would be back to the issue before. What's the length of bursting you would do? Well, that 11 1/4 degree bend would dictate whether you got an entrance and exit pit.
Okay, so the bends is one thing, but there was also the repair clamps and or fittings.
The repair clamps, depending on the repair clamps, they may catch up with you. If you remember that photograph that I had with the crumpled pipe in there, they may catch, they may not. If you put the blade on there and the repair clamps, it very likely could pull through and rip it. If the pipe downstream of that has got sufficient longitudinal strength. But if the pipe downstream of that is that very thin wall steel pipe as we have in that condition, you're probably not going to have enough energy, ability to hold that repair clamp in place as you're pulling a blade through it.
Okay, so I think then, in terms of can we pipe burst small diameter cast or ductile water mains, I think the answer is you can burst it, but you need to understand where the bends are and where the repair history is. And I guess my question sort of to add to that would be, a lot of our information on some of this old infrastructure that we want to replace is non-existent. They didn't keep great records back in the day. I'm sure that's shared among all the municipalities. So if you really struggle getting that information, is it worth the risk to pipe burst something when you're not 100% sure of where these bends or repairs have been?
Well, I would answer that back. If I'm bursting something that's 1880s, 1900s, 1940s even, it's cast iron. If it's cast iron, it's not an issue. Generally, pipe bursting is not an issue. Where it becomes an issue is when we get into materials that are ductile. And I don't mean ductile iron. I mean they've got ductility in them. In other words, it can be steel or ductile pipe. And back to the question that he asked a second ago, can I burst ductile or cast? Remember, one is splitting and one is bursting. If I'm cast, I can go from a 3-inch or say a 75 millimeter cast iron pipe, and I can easily pull in a 6-inch or 150 millimeter pipe, or even bigger than that if I really have to. But in ductile, if you remember that splitting that was happening, the splitting action doesn't cause the ductile to break into shards. And in lots of cases, you don't take the pipe, especially the bells and ductile pipe, you don't cause them to go into plastic failure. To put it, you know, you're just elastically deforming them, pulling the head through, and therefore they come back again. That's one of the problems with ductile pipe. Or to benefit the ductile from the point of view of loading and so on, but it's a problem from a bursting issue, is that you don't take it beyond into its plastic yield points. So it tends to elastically spring back again. And you can see that on the, I had that one picture there of the bursting head going through it. It yielded at kind of 9 o'clock and 3 o'clock and snapped, but the bottom stayed the same.
Okay, so I think, so there's, well, in Waterloo anyway, we have a lot of ductile iron, a lot in that sort of time frame when they switched from cast to ductile and our subdivisions grew.
But do you have water demand increases there, or are you just rehabilitating the pipes? I
guess I'm just thinking from like a general question, like in this situation where if you wanted a increase in capacity, you had a lot of 150 water mains, there's fire flow issues, you want some larger main. Is it worth it to consider that as an option if you have a lot of ductile pipe that has bad as built information?
You can. There are ways of finding out, of going in and assessing your pipes. I mean, it's not that hard to find out if there was a break in there and they put a piece of C900 in there 15 years ago or 20 years ago, and they dropped in, 2 lengths of C900. You can see it in conductivity tests. You can see it. There's various ways of finding out what's in there. But what I was going to say though is, Caroline, if you have ductile pipe, generally you're not looking to upgrade your diameters. There's lots of other ways out there of rehabilitating a ductile pipe, because ductile and even cast pipe is phenomenal product. It's a great product, and it will stand to be rehabilitated numerous times with either liners or sprayed on liners. There's lots of other ways of doing it, which are a lot cheaper than pipe bursting.
Yeah, for sure. And the city's definitely done some of those lining options. Well, we have here anyway. I'm more just thinking about the situation where you need to upsize. Yeah. Is kind of that scenario.
Yeah.
Okay, so definitely you need to do, if you think it's something you want to investigate, maybe it doesn't make sense to open cut something, or you have above ground issues, then maybe you need to do a bit more investigative work and spend that money up front.
You do. I mean, Murphy Pipelines is doing an awful lot of pipe bursting in southern US, in Texas, all through to Florida. They're going in and knocking off subdivisions in 2 and 3 days, replacing the pipe in 2 or 3 days with no issues down there. And that's shallow buried, not like northern US or Canada where you're 2.5 meters deep. They're just a meter deep or less than a meter deep, and very, very cost effective using pipe bursting. So it is very doable.
Okay, I'm getting that we only have one more question, but we have a few more. Okay, quick question for Allison. Is it possible to send out answers to questions we don't get to answer afterwards?
Yeah,
yes.
Of course.
Okay. So one more question then, and we'll send out answers after. Would pipe bursting be precise enough for upgrading your gravity sanitary main where the grade difference is very minimal?
So if you go back to that large burst that we talked about, the one where we went from 350 to 900, that's a very large burst. Those grades were 0.0, maybe there was a second zero in there. So essentially dead flat. Right? So you can pick your number, pick how flat you want it to be. Essentially, it was being pushed through with a surcharge through there, and afterwards there was ponding in there of 25 millimeters, which is nothing on a 900 millimeter pipe. And the engineer had the option to repair sags, but they chose not to do it. So it's very cost effective and very little disruption on the grades.
Okay, that's great. That's great, because yeah, there's a lot of very flat sewer pipes. Okay, so I think Allison's telling me we're out of time, and there are more questions here. So we will prepare answers. David, we can work together and get answers prepared, and I'm assuming Allison, you have the list of speakers. We can send those out. Oh, and a copy of the slides. I believe they'll be posted on the CUIIC website. Is that correct, Allison?
Yes.
Yes. Yep. They'll be on the CUIIC website afterwards.
Caroline, can I interject here? On the next slide down, if you want to go to, we can go down there. The next, yeah, my email address is there, and I have no problem if somebody wants to contact me privately as well. I'd be delighted to talk to them and advise them.
Okay, yeah, I think there could be lots more questions, but for today, we've gone over time. So yeah, we'll get the rest of your questions answered and we'll send it out for everyone. This is, at the end of the day, this is all about sharing our knowledge and helping the industry understand these different products better. So I think this is great that people are asking questions and that we had such great attendance. And I just want to thank you all again for coming. And yeah, keep looking for the next topics that are coming. There's lots of really great information on that note on a wide variety of all things underground infrastructure. Thanks.